Hello everyone and welcome to another video. Today I'd like to introduce the concept of time domain analysis. So to set the stage for what we mean by time domain analysis, I like to think about just having some kind of system. The system might have some inputs, let's call them U of t, and some outputs, Y of t. And for now, let's just consider these to be single input, single output systems. Now, we've seen that you can model a whole lot of different systems with differential equations. You can have mechanical systems, electrical systems, thermal systems, etc. Lots of them can be modeled by ordinary differential equations, right? Now, if you have some kind of mathematical model of the system, all time domain analysis is saying here is how can you predict some of the outputs given some of the inputs without maybe having to explicitly solve this differential equation, right? So if the input to this system is something like a step input, how can we maybe predict what the system is going to do on the outside or on the response, right? Is it going to look something like that? Is it going to look steeper here? Is it going to oscillate? That kind of thing. Similarly, you could also think about, well, what if the input was something different, right? If you had an input that was like a ramp, for example, right? How would the system respond on the output end, right? So all time domain analysis is saying here is we want to predict the behavior of the system as the independent variable here of time progresses, right? So in all of these cases, time is the independent variable, okay? I just wanted to bring that up here and sort of set the stage because later on we'll be discussing frequency domain analysis, which looks at when the frequency of the input changes and frequency is the independent variable. So in this case, all we're looking at is really just trying to predict the behavior of the system without having, again, to analytically solve this ordinary differential equation and plot it out here. Okay, so that's all we want to do here. And you know what? If you're familiar with ordinary differential equations, I think you may already have a feel for some of this here, and we might know some key characteristics of the system that would allow us to make these predictions earlier. So for example, you know, for ODEs, ordinary differential equations, right? I think we realized and we saw that poles play an important role, right? Right? So the poles of your system here, if you were to map these out on a real imaginary axis, right? We saw that depending on the locations of the poles, the behavior of the system is different. So for example, if you had a pole here, the response of your system here might look something like this, right? It's an exponential decay. But if the pole was further out here, we saw that you would have a sharper decrease, right? Similarly, if you had poles out here in the right half plane, your system, instead of being a decaying system, you would have a slowly exponentially increasing system. And similarly, the further out you push the pole here into the right, the quicker that exponential increases. And then we can extend this idea, say, going along the imaginary axis, right? If you kind of start taking some pole locations and having them out here, you start getting sinusoidal oscillations. And again, as you start moving these pole locations further out, right? We saw that what that tends to do is increase the frequency of these oscillations. And then again, if you start combining some of this behavior, like if you had a pole out here, you would have something that looked like a combination of exponential decay and sinusoidal oscillations, right? And similarly, let's finish out our picture. Something out here would yield sinusoidal increasing behavior, okay? So in this case, we saw that the poles here, if we look at the pole as being, the pole is something like an x plus a yi, right? A real and an imaginary component. We already have some idea of time domain analysis in the sense that if you were able to parameterize the system by the poles, you would have some rough idea or general behavior of the system depending on where these are. So the general behavior we had here was, you know, more negative x, right? what that corresponded to was what? It's a faster decay, right? Right? If you had a more positive x, this was faster growth. And we saw that the increased magnitude in y, right? This yielded faster oscillations. Right? So this is some flavor of time domain analysis here, but we would like to get a little bit more precise here and make a little bit more careful predictions on what is the system going to do here and how are we going to measure those performances. In this case, in this discussion, in this video, let's just focus on first order systems here. Before we get to that, actually, maybe what we should do here is let's discuss some of the differences between maybe the transient and the steady state response of a system, because we're going to see that both of these play a part here in our discussion of time domain analysis. So let's quickly talk about that here. We should talk just the terminology here of transient versus steady state behavior. Right, so if you watch some of our previous videos here on final value theorem and DC gain, I think you understand some of the steady state behavior, but maybe we should make sure we kind of formalize what we mean by transient here. And maybe formalize is a little bit strong of a verb here, because you can really sort of explain these using very general terms here, right? So the idea here is, your transient response is basically the process of going from the initial state to the close to final state. So let's say process of going from initial state to steady state. Right? And the opposite of that, well, actually not the opposite here, but kind of a the other half that we want to look at here is sort of the steady state behavior. So steady state. So this is how the system responds as t goes to infinity here, right? So as time grows large and some of these initial conditions or these homogeneous solutions die away, what does the system do here, right? So just to give you a very quick graphical example of this, right? Let's say you had some system here and it, again, was, maybe we can model this as a transfer function or some ordinary differential equation here, but you put in some input to this, like some step input, and the output might look something like this, right? So what it might look like here is you would have, I don't know, something like that here, right? So here's y of t versus t. Right? So in this picture, I would call, this portion of the response, it's not clear where it exactly ends here, but this is sort of your transient. Right? And then over here is sort of the steady state response. Right? So you can see the transient has something to do with initial conditions or a difference in the input and the initial state here. Maybe I should have drawn this with something like, maybe it has an initial, maybe actually down here. Let's do something like this, maybe with a negative. There we go. That's maybe a little bit more representative here, because now this shows that, you could have non-zero initial conditions and all this kind of good stuff. But at the end of the day, all of those initial conditions and their effects should die away, and you should end up with some steady state behavior, right? And in this case, you see that the system seems to go to a final value here. And again, this comes into that discussion where we had a final value theorem and DC gain of a system, but it doesn't have to be this way. So for example, your steady state behavior, it might not go to just a constant. You might have the steady state behavior of your system to be a function. So for example here's another example here. Why don't we also look at this same system here? Right, but now instead of putting in a step, let's put in like a ramp here, okay? And now what the output of your system might look like in that case, y of t versus t, is you still could have initial transient discussions here or inputs here, but hopefully this thing goes to some kind of steady state behavior. So again, your transient would be here. This was what I might consider the transient response. And now here you finally settle into steady state. So in this case, we can see the steady state behavior of your system is not a constant value, but almost like a function here, right? And just to further illustrate this, let's look at maybe one more case of transient versus steady state analysis here. So again, you got your system, but now let's put in maybe like a sinusoidal function. And now what the output might look like in that case is, again, you could have some kind of transient here where you would have some effects due to the initial condition, but eventually you would settle into steady state. And again, we see that the steady state behavior is not a constant, but it would be a function value. This one, maybe I kind of want to put a little bit of an asterisk behind it because we're talking about time domain analysis, and I think you can approach this in a time domain analysis sort of mindset, but this is exactly the framework for when we start looking at frequency domain analysis a little bit later here. So I just wanted to put this in the back of your head that time domain analysis, frequency domain analysis, a lot of them are, they're more intertwined than you may think here. And all they're really talking about is just predicting the behavior of the system without having to analytically solve the equations here, right? So you might wonder, do I really care about this? Is this really important? And the answer obviously is yes here, because if we're dealing with dynamic systems, both the transient and the steady state behavior are incredibly important, right? The reasons why you got to worry about this here is, if you think about this, your system usually has to run in steady state behavior for the majority of the time, right? So system must run in steady state the majority of the time. However, you need to be able to get to steady state behavior without failing here, right? So system must be able to get to steady state without failing. In other words, it needs to get through the transient response safely without failing here. So one kind of quote-unquote urban legend that I maybe heard when I was learning this, and when my professor was telling me this, is they give this example at I think back in the 70s or whatnot at our university, there was a fraternity here that had a balcony on the second floor here, and I think some students decided to try to start their own little bungee jumping expedition here, right? So what they ended up doing was tying a bungee onto this, and they weren't the smartest, but they weren't the dumbest students either here. So they knew they had to test this thing first. So what they ended up doing was tying a weight onto this, which was exactly the weight of the student here, and they tied the bungee to the top of the rail, and they lowered the bungee down here, right? And they figured, what would be really cool is if we could just bungee jump, and then we could just make it so that when we land, our head would just barely almost hit the ground, and it would look so cool if you could just bounce down there here, right? So here they tested it, and they got the length of this thing correct, so that at steady state, the bungee would hold their weight here, right? But they unfortunately didn't discuss here and understand the differences between the transient and the steady state behavior of the system. I'm sure you can imagine how this went really quite badly for the student, right? Luckily, I think there were some bushes down here, so I don't think this was anything horrible. But, at least... well, on the plus side, I don't think he was accelerating anymore by the time he hit the bushes, right? But he neglected to take into account the differences between the transient and the steady state behavior. And what we want to do with time domain analysis here is understand, is there a way that we could have predicted how much overshoot or how long it would take to settle or things like that before you actually go out and build your system here, all right? All right, here we are on top of the second floor balcony. Let's measure out how much rope we're gonna need to make this bungee jump. I think I remember something from my statics class saying that at steady state equilibrium, the force from the bungee should equal to my weight. So let's just go ahead and lower myself down slowly. And once I reach the ground, that'll tell us how much rope we're gonna need. Here we go. All right, keep it going, dude. A little lower, a little lower. There we go, that's perfect. Look at that, dude, this is gonna be so sick. This is exactly the right length of bungee cord we need so that it's steady state equilibrium. We're just gonna be hanging right here above the concrete. Okay, let's bring it back up, dude, and give it a try. All right, here we go. Wish me luck, dudes. Cowabunga! Uh-oh. Okay, so we saw why the transient analysis in combination with the steady state analysis is important. So what I want to do now here is let's just consider how about first order systems. And look at doing time domain analysis for just this type of system. Later on, actually, in one of our following videos, we'll talk about second order and higher order systems here, but I think it helps to start just with the simplest system and work our way up from there. So with the first order system, let's just consider a general first order system that might look something like a y dot of t plus b y of t is equal to some c r of t. Okay, so again, if you want to conceptualize this system, it's this differential equation where you have r of t as an input, some reference signal, and y of t coming out the other end as the output. Okay, so we can easily compute the transfer function of this system here. So transfer function of the system. Right, that is going to get us, let's see, if we Laplace transform both sides and neglect initial conditions, we get a s y of s plus b y of s is equal to c r of s, right? And I think if we solve now for the transfer function, which is the output over the input, we could get this thing to look like a c over as plus b, okay? So here's what our system looks like. So maybe the other way we could represent this is instead of just calling this system here, maybe we call this thing c over as plus b, right? The thing I do want to mention here, and maybe keep in the back of your head here, is if you remember here with our transfer function, we neglected initial conditions here. So we will come back to that in a second and show that actually this is a no real consequence, but maybe let's put a little asterisk here and note here that we neglected initial conditions, all right? Okay, so what we can do here is a couple of things here. So first off, let's maybe make a quick note here that the DC gain of the system, right? Remember from our previous video here where we talked about DC gain here, we saw that you can obtain the DC gain of a system by just taking its transfer function here and evaluating it at s is equal to 0. So we see that the DC gain of this system is not unity here, right? It's the c over b, okay? Let's just keep that in the back of our head here. Okay, so what we can also do now is let's start looking at the performance of this system here, or some metrics that might quantify how does this system behave in both transient and steady state. So one of the steady state parameters we can look at here is how about steady state error? In other words, how does the output track the input here, right, at steady state? So from our previous, again, discussion here where we talked about DC gain, we saw that the steady state error of a system in response to a step input here for any order system, first, second, whatever here, is this here, right? So this is steady state error, and I guess maybe we should quantify this here with respect to step of magnitude A. Right, that magnitude here. Okay, so we just put this in here. So we already have the DC gain. So we have this is 1 over c over b times a here, right? So here's our steady state error. Okay, so I guess you could box that up and you could say, you know, here's some performance metric, or here's some prediction of the system that we didn't actually have to solve for it. If you know these c, b, and a, you can plug it in right away and you can understand what's the steady state behavior, the steady state error of the system. Right? Now, let's look at something that's a little bit more interesting. And tell you what, maybe let's erase this so we get a little bit more real estate here. Let's, how about look at what we're going to call the settling time. And maybe let's call this TS. Okay? So what the settling time is it's basically the time required for the system to reach within a specified bound. Let's call this bound delta of the final value. Okay? So the picture that goes along with this here is that if you have a first order system here, we know what this is going to look like here is you start at some initial condition y0 here, right? Some initial output, and this thing is going to go to some steady state value here, right? We just saw that it has a DC gain here, and what we're going to do here is this is eventually, assuming that the input is a step input, right? This is going to do something like this. It's going to asymptotically approach this, right? So what we see here is that there is a bound here, or there's a change in signal here going from going from the initial condition to y steady state. Let's call this distance here, how about delta y, your change in output signal, okay? And what we're looking for now is when does this response of the system reach some bound? Maybe I'll draw it like this, and it can go plus or minus here, I suppose, if you're coming in from maybe the other side here, right? So this distance between the steady state value to one end of this bound here is delta times, well, gosh, I guess I'm using deltas wrong. Lowercase delta, which is the bound here, and times capital delta y, right? So this entire region here is 2 times delta times delta y. Right? So the settling time is this point right here, when it first reaches within this bound here. So the settling time is this value here. Again, obviously assuming that everything starts here at time 0 here, right? Okay, so maybe one other thing that would be helpful with this picture here to note here is that if this is delta y and this little region here is little delta times big delta y, then the distance here, this right here, I think we'll all agree is 1 minus little delta times big delta y, right? Okay, great. So what we need to do here is solve for settling time, okay? So the first thing we need to do is let's get this curve here of y of t versus t here, okay? So to do that, let's go ahead and get y of t. So to do that, I want y of t, right? To get that, what we're going to do is we are going to take the system here. Where was I here? Oh, okay, yeah. So where did I put the initial condition part? Oh, okay. Well, no, sorry. Tell you what. Let's do this first. We're going to get to the initial condition later. There's more than one way to skin this cat. So let's just first look at this from just geometry. Well, I guess it's not really geometry here, but from all of this. So we saw that here, y at the settling time, right? Y at the settling time, where is that? That is, maybe I'll use red. Actually, no, we've already got the green here. That's this value right here, right? So this here is y at the settling time, right? So that value here, I think you'll all agree here, it's y0 plus this distance right here, which we just said was 1 minus little delta times big delta y. Right? Okay, and now let's go ahead and note here that big delta y, right? We said it's this big distance, right? So it's y steady state minus y0. So it's y steady state minus y0, your initial condition. Okay, so let's plug that in here. Okay, so we end up, this is y0 plus 1 minus little delta times, where did I have this? Y steady state minus y0. Okay, so let's rewrite this here and let's FOIL this out here. So we get what? Y steady state minus what? Delta y steady state minus y0 plus delta times y0, right? Okay, great. So some of these cancel. This cancels with this here. And this, I think we can rewrite this thing as what? 1 minus delta times y steady state plus delta y0. Okay, great. And now let's go ahead and how about let's assume that the system starts with no initial conditions here, right? And again, maybe put another asterisk in here because we're basically neglecting initial conditions here again. We'll look at an example in a second where we don't neglect initial conditions, but to make things easier, let's just do this for now. So this term can go to 0 here, okay? So we're almost there here. The last thing we need to do here is, if this starts here at 0, let's get an expression for the analytical curve right here, the actual response of the system, okay? So to do that, right, we can actually come back here to our transfer function of the system, right? Because the transfer function neglects initial conditions and does exactly what we want. So I have a step input of magnitude, I guess A in this case here. Let's say that this delta y here is a step of magnitude. Oh, no, sorry, excuse me. That's not delta y. The input here is a step of magnitude A here. So let's go ahead and get that response right now. So what we can do here is we can get this in the Laplace domain quite easily here, right? So the output here, the step output is going to be the transfer function times an input step here, right? So A over S here. So this is here step of magnitude A. Right, so that is going to give us this curve here. So again, just plugging this in here, we've got C over AS plus B times A over S. Right, that's what we end up with. And to get this thing back into the time domain, we're just going to inverse Laplace transform all of that. I'll assume that you can do this. You can run over to Mathematica if you like and just literally put in inverse Laplace transform of this expression and go from the S to the time domain. And we will end up here with the time domain response of this system, which, if you're terribly interested here, is given by, it's going to be A times C over B times 1 minus e to the minus b over a t here. Okay, so that's the expression here. While we're at it, let's also get the term for y steady state here. So while we've got this here, we can note here that y steady state, there's a couple ways we can do this. We either apply final value theorem, or we can just go ahead and take the limit as t goes to infinity of the expression that we had right above, right? And we notice here that if you assume that A and B are chosen in such a fashion that this quantity here is positive, so basically I want this negative exponential, basically let's just say assume that A and B are both strictly greater than 0 here. You see that this exponent goes away and we end up here with that the steady state value of this system is AC over B, right? Okay, so great. We can now plug that into the left-hand side of this here, right? So, sorry, we're running out of room. Tell you what, so to make this not as super confusing, let me just go ahead and write it up here. Okay, so the left-hand side of this expression here is the equation of this curve, but everywhere you see t, plug in the settling time here, right? So there's the equation of the curve here, right? So I got capital A times C over B times 1 minus e to the minus b over a times settling time, right? Okay, that's the left-hand side right here, right? And this is equal to, what do we got over here? We end up with just 1 minus delta times y steady state, which we said was this quantity here, right? A C over B. Great, okay, so these cancel here. This is actually looking quite nice here. We end up with just here. It's this 1 e to the, oh, actually look at this, and even the 1's cancel then, and actually I can then just put a plus sign on both of these here. So basically this boils down to the e to the minus b over a settling time is equal to delta here. So take the natural log of both sides, and with a little bit more manipulation you can then solve for settling time here, and we get that the settling time here is negative a over b times natural log of delta here. So in this case, delta is in the range of 0 to 1. Actually, I guess we should probably make these not inclusive bounds. so we don't run into any infinity. So here's our expression for settling time. So great. This is really awesome because now if you have a settling time, like for example, you want it to be within, say, 2% of the final value here, you would choose a delta of 0.2. So this corresponds to 2% of steady state value. Right? That's great. Okay. And again, the thing that might be going clang in the back of your head here is that we made this assumption that the initial conditions are not zero, but surprisingly, we're going to show later in an example that this result is still true as long as you define the change as being the steady state value, the difference between the steady state value and wherever your initial condition is. So luckily for linear systems, this thing still holds even if your initial condition is not zero. Okay, so that's great. So this gives us an expression for settling time. Let's look at one other expression. How about rise time? So rise time is defined very similarly to settling time, but it's basically asking how long does it take the system to get to a certain value here. So let's talk about this real quick. So rise time, let's call this TR. Okay, so this is basically TR. This is defined as the time it takes for the signal to reach a specified value or specified percentage of steady state, right? So in this picture with the first order system, if you think about this long enough, the picture is identical here, right? There's actually no difference between settling time and rise time here, right? So rise time you could easily, this is settling time or rise time. So basically, the derivation is the exact same. You're still looking for when does this signal, how long does it take to get from the initial condition up to some value here. The only thing that's slightly different here is that delta, again, is typically referred to, is going to be in the range of 0 to 1, not inclusive here. And what this means here is a delta of 0.9 is basically saying go from 0 to 90%. So basically, the delta in the rise time case is basically 1 minus the delta in the settling time case, right? So the result is the same here. We just define delta a little bit differently because typically people will talk about, the 90% rise time is the same thing in the first order system as the 10% settling time here, right? So really, rise time is the exact same here. It's minus A over B, natural log of now 1 minus delta here. And again, delta is in 0 to 1. Maybe we should have little different deltas here. Like this is delta for rise time, and this is delta for settling time. Maybe that makes a little bit more sense here, right? But it's basically the exact same thing, right? Okay, great. So again, this result here was in response to a step input of magnitude A. Why don't we go ahead and repeat some of this analysis and look at how does a first order system respond to, say, a ramp function. So give me a minute, I'll pause the video, erase the board, and we'll come back and look at a ramp. Okay, so why don't we do the same thing and look at the first order system response to a ramp. Okay, so now exact same picture here where you've got our system G of S here, but now let's assume that the input is actually going to be a ramp, something like AT. Okay, and now I want to get the response here and do a little bit of time domain analysis on this system here. Okay, so the way we can go about doing that is just like we always have. Let's go ahead and compute first the response of the system here. So y, I guess, in the Laplace domain here, that's just G of S times the ramp here, which in the Laplace domain is A over S squared here, right? So again, you plug in your G here, and what we would then do is go ahead and do the inverse Laplace transform of what we end up with here. So I'll spare everyone the algebra here of doing this. Again, run over to Mathematica to do this if you'd like, to get ourselves the response of this system in the time domain. And if you do that here, what you would end up with here is y of t is going to look something like AC over B times t minus A AC all over B squared plus AAC over B squared e to the minus B over AT. Okay, so here's the response to the ramp. Okay, so again, what's interesting is if we assume that A and B are both strictly positive, right, at steady state, this term goes away here, right? So we see that Y steady state is actually a function of time, but it looks something like this, right? AC over BT minus AAC over B squared, right? Okay, so here's the steady state behavior. We notice here that it is not a constant value, right? It's basically, this looks like y equals mx plus b here, right? So it looks like an affine or a linear line, right? Okay, so now what we can do here is let's go ahead and look at the steady state error. How about, how does the steady state output differ from the from this input here, right? So the error in steady state, right? We said that that was r of t minus y steady state of t here, right? And we know here that the input reference was a ramp, right? So this is AT minus the steady state error, the steady state response, which is this down here, right? So this is minus quantity AC over BT minus AAC over B squared. Okay, so you simplify this thing down and you can basically get this thing to be massaged down to look like big A minus AC over B T minus AAC over B squared here, right? So again, this is in response to a ramp, right? So you notice here a couple of things. The steady state error has the potential to actually grow here in some situations. So what that would mean here is that if your input here was something like this, here's R of t, your steady state behavior, y, it might do something like this. And the error at any given point might just grow here, right? What's interesting here is if you notice here, if C over B was 1, this would be gone, and we would end up with just a constant steady state error here. What's actually even more fascinating here is if you remember that the DC gain of the system, that was G0, that was actually this quantity C over B here. So we can see that if your DC gain is unity, basically 1 here, what we end up with is in response to a ramp, you end up with constant steady state error. In all other cases, if the DC gain is not unity, your steady state error is actually going to be growing here, or potentially, I guess, shrinking as well, but won't. Yeah, well, let's just leave it at that, right? So I want to look at an example now here. Let's look at a real physical system. We'll examine those two cases that we just did. One, subjecting the system to a step input, and second, subjecting it to a ramp input. So to set the stage for these examples, tell you what, let's pause the camera here, get away from the whiteboard, and we'll actually head over to the stove. Okay, so I'd like to explore a real-life responsive system to a step input. So the system in question here is a thermal system. We are going to have a pot of hot water. You can see I've got the water boiling over here. I'm going to pour it into this pot. So this pot will be at some temperature. And then I'd like to have some kind of thermal sensor, like a thermocouple or something like that, that is at a much lower temperature. And then I'm going to dump it into the hot water, which is basically subjecting that temperature sensor to a step input. So why don't we go ahead and do this real fast. Let's go ahead and put on a little hot mitt here, and let's go ahead and pour in the water to the, whoa, crud. Whoops, all right, don't tell anybody about that. Okay, hold on, it's going, there we go. The water's hot, it's boiling. Okay, so we got the hot water here. Let's turn off the stove. Okay. So now what we want to do here is, I wish I had a thermocouple. I guess I don't here. As you know, a thermocouple is just a temperature sensor here, right? So what I want to be able to do is dunk it into here and watch the temperature increase. But since I don't have a temperature sensor here, or a fancy thermocouple, I guess what I can use is Here, let's just use my gloved hand. I'll just dunk it here into the hot water here. I don't think anything's really going to be that bad. But as you can see, my hand here, right, is at normal body temperature. The water is at much higher than body temperature, so I'm basically going to be subjecting my hand to a step input in temperature. And hopefully the transient thermal conduction and the dynamics that are going to have to go from having the heat go from the water through the mitt to my hand will be slow enough that I'll be able to feel it increasing, but it's not going to really, hopefully I'll be smart enough about this. Okay, so let's try this. So ready? So here we go. Now, ready? I'm going to subject my hand to step right. 1, 2, 3, go. See, that's pretty fine. See? Oh, but I can feel it getting warmer, right? It's getting a little bit warmer. Yeah, but see, it's not much, right? So it's asymptotically sort of increasing. I think we're gonna model this here on the board a little bit. Oh, and now it's getting warmer. Now it's getting a little bit warmer. Now get it warmer. Get warmer. Okay, so we saw the motivating scenario here. So let's go through that example real quick. So again, the example I want to model here is a thermocouple response. And the first case that I want to look at here is the one we just did here. So let's look at a step input. And we'll do some time domain analysis on the signal there. So again, the picture that went along with this here is we saw there was a pot of hot water here. And, you know, this thing, as we saw, was kind of hot. Let's draw some steam coming out of it. And we have our little thermocouple. And as you guys all know, a thermocouple is just a small little piece of dissimilar metal here. And let's say that this thing has an initial condition here of maybe 5 degrees Celsius. Okay? And down here, this is our hot liquid. And let's, for the purposes of this problem, let's just say that its temperature, let's call it T infinity here, is going to be, let's call it 400 degrees Celsius. Obviously, that's not what we just had here, but that's what we're going to use for our example here. So some thermal properties of all of this system that are going to be related here or relevant here. So properties of the thermocouple. Some constants that we're going to care about here is K, this is the material's conductivity here, so whatever it's made out of, let's just assume that this is 20 watts per meter Kelvin. So again, this is the material's conductivity. Okay, the specific heat, let's call that capital C here. This is going to be 400 joules per kilogram Kelvin. So this is the specific heat. Okay, so the density of this metal here, let's call this, for the thermocouple, is 8,500 kilograms per meter cubed. So again, this is the material density here. And let's call the diameter of this 3 millimeters. So this is our diameter of the thermocouple. Okay, and we'll say that the initial condition of the thermocouple here is at 25 degrees C. We better convert that here to an SI unit of 298 degrees Kelvin. So here's our initial temperature. Okay, and then there's some properties of the water or the liquid that we probably care about as well here. So for the liquid, I guess I'll do it up here. Gosh, I wish I could have use the space a little better and kept everything in one spot, but all right, whatever. Let's put it right here. How about for the liquid? Some values that we're going to care about here is the convective heat transfer coefficient here. Let's call that thing H here of 400 watts per meter squared Kelvin. So this is the convective heat transfer coefficient. Okay, and then the temperature here of the liquid, let's call that thing T infinity, is again 400 degrees C, or I guess turning that into Kelvin here by adding 273 will get us up here to 763 degree Kelvin here. So this is the liquid temp, the temperature. Okay, all right. So before we jump into the equations of motion here, or at least the ordinary differential equation that we can see is going to model this simple system, let's calculate a couple of secondary parameters here that we're going to need here. Okay, so secondary parameters, things like the volume of the thermocouple here, right? That's just our good old friend 4/3 pi r, which is, I guess, diameter over 2 cubed. And again, maybe we should have converted that diameter. We probably should have put this in meters. What is that? This is divided by 1,000 to get it in meters here. But anyway, you crunch this number here, you end up with the volume of this thing is really small, 1.413 times 10 to the minus 8 meters cubed. And I guess the surface area might be also good to know here. So let's call that AS for the surface area here. So that is our good old formula for a sphere. Again, maybe what we're doing is we're assuming that thermocouple is just a sphere here. So this is 4 pi over r squared. So again, you crunch that number, and I think you come out to 0.1234028 meters squared. Okay, so we've got some of those things. Okay, great. So getting the equations of motion here, it's outside the scope of this discussion here, but you can basically see, I'm going to post another lecture here on dynamical system modeling of thermal systems. And as you probably know, you may have seen some of the other lectures here where we talked about thermal systems being a partial differential equation, right? Because it relates both time and space. But if the system is simple enough, like it is in this case, and one-dimensional enough, the spatial component comes out, and you can actually model this scenario that we've got right here as just a simple ordinary differential equation here. So, or sort of an ODE. So, again, that's outside the scope of this system here, or this lecture here. So I'm just going to write up what the equation of motion is going to be that you would come out with here. So basically what you would get here is the temperature of the thermocouple, capital T of T. That's what we're interested in, right? Its temperature is related to or is written down as a differential equation, right? So we can say dt, crud. T is that's going to be a little bit hard. Capital T is temperature, lowercase t is time here, right? Okay, this plus beta times temperature of time is equal to beta times T infinity. That's about it, right? Okay, so this is an ordinary differential equation. So again, in this case, T of T is the temperature of thermocouple, right? T infinity is the quote-unquote the step input in temperature, right? Because you drop this thing into this hot pot of 673 degree Kelvin liquid here, right? And then finally, beta is this coefficient that if you had done all of the thermal analysis, you would get this beta coefficient, which is basically a mishmash of all of these constants put together here, right? So this is going to be H times the surface area all over rho V times the specific heat C. Okay, so again, in our case here, maybe what we should do here is let's specifically write this out, because you see beta is just going to be this constant here. So H here, right, was the convective heat transfer coefficient of the liquid here, right? So this is 400 watts per meter squared Kelvin, right? AS was the surface area of the object here, or the thermocouple, right? So that was just a lot of zeros there. I want to make sure I get all of this right here. Where did I have this thing actually? Well, okay, anyway, let's just do this. 0.00028 meters squared. All over, the density of this thing was something really small. No, sorry, I was pointing to the wrong thing. Where's the density? Oh, no, here. Actually, no, the density was large, right? It's metal, right? I think it's pretty dense. 8,500 kilograms per meter cubed, right? Times the volume of the thermocouple, which we computed right there, right? 1.413 times 10 to the minus 8 meters cubed. And then times C, which was our specific heat of the thermocouple here, right? Which was 400 joules per kilogram Kelvin, right? Okay, great. Now, what might be actually very interesting to do right now is obviously go ahead and compute all of these here. So the numbers you come up with here is this is going to be actually it's 14 over 17. So it's 14/17 is that number. What's more actually interesting is maybe the units of this guy. Maybe let's look at all the units and what does this come out with here. So let's see. This cancels here. This cancels. This cancels. This kilogram cancels. That cancels here. So what do we end up with here? Let's just focus on the units. So this is watts per Kelvin all over joules per Kelvin, right? So this is, again, just focusing on the units here. So it's watts per Kelvin, kelvins per joule, right? So the kelvins cancel out here. So we end up with watts per joule. Now, if you remember, what is a watt, right? A watt is a joule per second here, right? This divided by a joule, so this cancels out. So interestingly, beta comes out to units of 1 over seconds. So what we end up with here is beta is actually 14/17 1 over seconds is the units here, right? So here's beta. Okay, great. So if we've got that, we can basically, we're off to the races. So let's look at this differential equation here and just do a little bit of analysis here. So tell you what, let's erase some of these some of this stuff over here. Okay, and maybe what we can do is let's get the transfer function of this system here, all right? Because we're looking at the step input. It might be reasonable. Oh, and actually, sorry. Maybe what I should have done, maybe over here in the differential equation, maybe I should have written, this is T infinity of T here, right? It's the temperature of the liquid, which could be changing, right? Later on, we're going to look at the case of a ramp here. This doesn't have to just be a constant here. We've got our minds so wrapped around the constant, so I dropped the sub T notation, but we really should say that this is the input, right? This is the input to the system is the temperature of the liquid, right? Okay, so the transfer function of this system, right? What we can do here is we want to get our transfer function g of s, right, where the input to the system is T infinity, right, and out of this comes the actual temperature of the thermocouple here, right? So I think it's really easy, just Laplace transform that guy. In the interest of time, let's go ahead and skip all of those steps because I think you've seen it many times before, right? Just Laplace transform this and solve for the ratio of T of T over T infinity, of S, we're in the Laplace domain now, right? Okay, so the transfer function you're going to get is just beta over S plus beta. Great. Okay, so a couple of things we can do right off the bat of this thing is let's get the DC gain, right? This is just G of 0. So if you see this, this is just beta over beta, so this is just 1 here, right? So the DC gain is 1, which again, kind of makes sense if you think about this, right? So if you drop this thermocouple or subject it to some temperature and you let it sit long enough, eventually the temperature of the thermocouple will come and equalize to the temperature of the liquid. So that's what this DC gain here is telling you, right? So also, in a similar sense, we could also look at the steady state error of this system, right, in response to a step. And we said this is just 1 minus G0 times the magnitude of the step here, right? And since this is 1, we see this is 0, right? So again, same thing, it's telling us the exact same story as the DC gain told us, is that eventually there's going to be no steady state error and the output will equal the input, right? Now, that's fine and dandy at steady state, but the whole point of time domain analysis is we want to know how long is it going to take us to reach that steady state here. So how about let's calculate settling time. Right? So we said settling time, right, was our earlier expression for this was it was minus a over b times natural log of delta here, right? Where a and b were coefficients of your of the differential equation here. So a was a coefficient of the derivative term. This was b, that was c here. So we see that this is what? It's minus 1 over beta times natural log of, for delta, let's go ahead and use, how about 0.02 here, right? So what we're saying here is that I want this thing to settle within 2% of final value, right? Okay, so beta, we already know what beta is. It's 14 over 17. So you put this thing in here, you crunch this numbers here, and at the end of the day, what we end up with here is 16.62. And again, let's think about the units here. We said the units of beta were 1 over seconds, right? So the units of 1 over beta should just be seconds, which makes sense because we're calculating a settling time here, right? So great. Theoretically, you dump that thermocouple into that pot of super hot water, and if you want it to get within 2% of its final value, you got to wait 16.62 seconds here. How about rise time, right? Okay, so rise time we said was a very similar calculation here, because for our first order system, right, settling time and rise time were basically the exact same thing here. So again, it's minus a over b times natural log of 1 minus delta rise, right? The only difference was now this delta here for rise time means something a little bit different. So again, here's our coefficients, minus 1 over beta times natural log of, how about let's use 90. So we want to know how long does it take the system to go from 0 and rise up to 90% of the final value. So I put in, I want 90% rise. Okay, so again, you crunch all these numbers here and we end up with a similar answer. So we end up with 9.79 seconds, right? So this is our rise time. Okay, so great. That's what we end up with. And again, if you went over to Mathematica, and I'm not going to do this right now because I don't want to break our stride here, because I think we're really trucking along here, and this is some interesting analysis here. But if you went over to Mathematica here, right, and you plotted the output of this, to tell you what, let's just do this here. I'll write out the very simple Mathematica code that I want to do. And feel free to plug this in if you want here, right? So you've got your g of s times the step input, right? Which was t infinity here, which I think we said was 673, right? Over s. This is a step input here, right? So this term right here is a step input of magnitude 673 degrees Kelvin here, right? This is going to give you y of s. Or sorry, not y. In our terms, this was capital T of s, right? That was the temperature. This is how the temperature of the system responds to this kind of a step, right? And then the next thing you want to do here is inverse Laplace transform T of s, going from the s to the time domain here, right? This would give you, oh gosh, we ran into like a variable collision here. Let's call it temperature as a function of time, right? And if you were to plot this thing, right, you would see it would start at 0, right, because we're using a transfer function here. So the transfer functions have no initial conditions here. And to get up to 673 Kelvin, it would do something like this, right, where it would asymptotically approach this. And according to our calculation here, to get within 2% of the final value, right, this delta here, this is 0.02 times 673, right, because that was a change here. This time right here was going to be 16.62 seconds here. And the rise time to get to 90% of it, which is another line, maybe I should have done that in a different color, just to make this a little bit more visible here. Maybe let's do this in green, right? This here is, I guess, 0.1 times 673, right? Because that means this rise here is a 90% rise, right? So this time where it crosses that line, this was our 9.79 seconds, right? Okay, great. So again, everything would look good here, but maybe the one thing that's now kind of hopefully in the back of your mind that's making you scratch your head or maybe giving you a little bit of pause here is the concept of, we started here at 0 here with this analysis with the transfer function here, right? And if you recall, the way we derived these expressions for rise time and settling time were assuming 0 initial conditions. In this case, though, the initial conditions were most definitely not 0, right? I actually, boy, if you could get the initial conditions of this thing to be exactly 0, I think you're in for some Nobel Prize of something, right? Like, I don't think you can get the thermocouple down to absolute 0, right? It started at 25 degrees Celsius, which was, I don't know, 25 plus 273 Kelvin here, right? So let's actually look and see that, you know what? It's actually not going to matter here. What I mean by that is, let's draw a similar picture here that more accurately represents what we want for our system, which has a non-zero initial condition. So again, maybe keep maybe we should have labeled this here. So this was our settling time and this was our rise time. You can think of these as using 0 initial conditions. Now, what's more accurate here, like a better picture of what reflects the physical system And the experiment that we did over there in the stove here is, again, you got time on this axis, you got temperature on this axis, but the thermocouple started at some time 0 here of some initial temperature, right? It started here, and we know that it's still going to go up here to T infinity, right? To the step input. So again, let's draw this asymptote, right? And now we know this is what it's going to do. Right? So this is more accurate. So in this picture, I might want to ask, what's the rise time and what's the settling time? Okay. So now the only thing that's different here is, and I hesitate to use the word different. It's really just a difference of how you would go ahead and define the change. As long as we define the change as from where you start to where you end. So in other words, this distance, maybe I should have, boy, I should have came up with something a little bit better here. Okay, but this, right? Let's call this your total change delta temperature here, right? And now maybe let's look like at the rise time. Maybe that's the easiest one here, right? Let's look at the rise time with initial conditions here, right? So what we're looking for here is using our green again, which is over there, is, okay, as long as we define this rise as a percentage of the total change, we're going to see we end up with the same answer. So in other words, what I want to look at is this distance right here, right? This is going to be 0.9 times delta temperature, right? Okay, and then where it crosses this point, this is going to be my rise time. Okay, now the question is, what is that value here? Okay, so to get that here, what we need to do here is, again, let's go ahead and basically write the equation here, assuming there are non-zero initial conditions, right? So if you recall, whoops, right? The equation of this black asymptote here, right? The way we would get that is, instead of using the transfer function approach here, right? Instead of using this approach, right? This approach has 0 initial conditions because we've got a transfer function here, right? Instead, what I would do is I would do the full Laplace and not make any assumptions about the initial conditions here, right? So in other words, what you would end up with here is temperature as a function of time. This is going to be T infinity plus the initial condition in temperature minus T infinity times e to the minus beta t. Okay? So this is the equation of the black line here, right? This is the temperature at any given time t. Okay? So the temperature at the rise time, let's call it TR. What did I use here? Maybe let's call it lowercase t so we don't end up with so many these things. So, no, actually, shucks. Yeah, tell you what, let's go with this because this is what I've got in my notes here. This is really what I'm trying to do here. I want to look at it here, okay? So this time, so I'm looking for the temperature at this time. So in other words, I want this y value up here, right? So there's 2 ways we can get that. One is I can take this expression here, right, and just plug in everywhere I see lowercase t, plug in lowercase tr. So this is T infinity plus T0 minus T infinity times e to the minus beta t rise, right? Okay, the other way I could get this y value here is this y value, it's just this T infinity plus 0.9 times delta t, right? So I could also write this is also, wait a second, where did I, oh, right, yeah. So this is also T0 plus 0.9 times times delta t, big delta t, right? Okay, now what is this delta t, right? If you look at this picture here, this big delta t is just T infinity minus T0, right? So this is T0 plus 0.9 times T infinity minus T0, right? Okay, so now what we end up with is this left side. I guess if you muddle all this through the right side, this you could also write as 0.1 times T0 plus 0.9 T infinity, right? Okay. is equal to, let's just copy the left side. T infinity plus T0 minus T infinity e to the minus beta rise time, right? Okay, let's, wait a second, what did I do with the e to the, oh yeah, okay. All right, so let's take off T infinity, subtract T infinity from both sides here, right? So this left side is just T0. I guess I can get rid of this parenthesis. I don't need him anymore because I'm subtracting that off to minus, oh no, sorry, I do need the parentheses, right? Because I'm trying to hit this whole thing with e to the minus beta TR, right? Okay, 0.1 T0 plus, what do we end up with? No, so we end up with a minus, right? So this is minus 0.1 T infinity, right? Because I subtracted 1 T infinity. There's already 0.9 T infinity on this side, so I end up with a minus 1 T infinity. Great. Now let's divide both sides of this to solve for this E term. And maybe I'll do this right over here, so we can keep both pictures up here. So we end up with e to the minus beta TR is equal to 0.1 T0 minus 0.1 T infinity all over T0 minus T infinity, right? Okay, so I think we're there because, I mean, if you take the natural log of both sides here and you simplify a little bit, I'll skip these couple steps, but I think we're basically there, right? I'm trying to solve for this TR. So I'm going to take the natural log of both sides here, get that beta on the other side here, and what we end up with here is TR is going to be natural log of 10 all over beta here. So again, all you got to plug in is your beta. If you remember, that was 14/17 in our case. So you plug all this number in here and you end up with 9.79 seconds. Okay, so this over here, 9.79 seconds. And again, you compare these two, right? The settling time, or sorry, the rise time with the initial conditions and the rise time with no initial conditions are the exact same values here, right? So what's really awesome about this thing with the linear system is that the calculations of rise time and settling time here, they don't matter if there are initial conditions or not, as long as you are correctly and carefully taking into account how you define the change in the signal, right? The change in the signal to a step is always the difference from where you start to where you end. It's not always from 0 here, right? Okay, great. So in this case, I think we looked at the response and the time domain analysis of the system in response to a step input in temperature. Why don't we actually look at maybe like another input? How about a ramp? Okay, so we're back here again, and I know what you're thinking, and no, I'm not going to do it again, right? In the words of former President George W. Bush, right? Fool me once, shame on you, but I guess you can't get fooled again, right? So we learned that a step input to this system, has interesting consequences. So instead, why don't we try to subject this system here to a different type of input, like a ramp input? So what I've got right now is the water is actually cold, right? So I can put my finger in here without a glove here, and it's totally fine here. But now what I want to do is let's subject the system to a ramp input. In other words, let's increase the temperature of the system linearly. So I'm just going to crank the stove on. There we go. So it's on, and the temperature is increasing. And now let's go use our thermocouple here, our poor man's thermocouple, which is this little junky mitt here, and my finger sensors, which have now hopefully gotten a little bit better. And I'm going to dunk it in here, and now we are going to subject the system. There we go. Now it's subjected to a ramp input here, right? So the question now is, how is the temperature of the thermocouple, aka my fingers here, right, related to the actual temperature of the water here, right? Is there any steady state error? Is that error growing here? It's a different kind of input, right? It's not a step input, it's a ramp input because the temperature of the water is increasing slowly and at some kind of rate, right? So that's the question that we want to maybe model on the board. So tell you what, let's go run over to the whiteboard here and model this system here. So let's do that. Okay. Ow, ow, ow. Okay, so now let's look at scenario 2. And this was the ramp input. So So again, the picture that goes along with this now is now we've got our pot of water, but now instead of it just being instantly hot, we're going to light a fire underneath this thing, and we're going to heat this thing at a rate of 5 degrees Kelvin per second. Right? And then what we're going to do is we're going to put the thermocouple inside. And again, the thermocouple has an initial temperature of, let's use the exact same thing, 25 degrees Celsius, which when you add that to 273, you get Kelvin. Okay, so this system, again, we're going to look at it as modeled as our transfer function here, or our dynamic system here, where now the input temperature T infinity is now a ramp. And I want to understand, what does the output temperature, or the temperature of the thermocouple, how does that track the input here, right? So let's apply the time domain analysis that we derived earlier. And if you remember, the steady state error that we showed in response of a first order system in response to in response to a ramp was A minus A over times C over B times time, right? Minus A C over B squared, right? So this was first order cis response to ramp of magnitude, or I guess of maybe magnitude is maybe a misleading term, ramp of slope A, right? So in our case, we have A as 5, right? It's 5 degrees per second here. Little a was 1. I think that was the first coefficient of our differential equation. B was beta, and C was beta here. So, and again, I think beta was 4, was it 4 or 14th? 17th. I always forget this here. I better make sure we get this right. What did we calculate beta to be here? Beta was, yeah, 4 over 17, okay? Great, so just plug all that in, and again, we make the note here that the DC gain of C over B showed up. We showed the DC gain was 1, so actually we see that the steady state error in response to a ramp is actually not going to be a function of time. This is all going to go away here, and we're going to end up with a constant value. So again, plugging and chugging all of these numbers in here, you get E steady state is going to be, what's the actual number you get? I think it's something like 21 degrees or something like that here. I just want to make sure I get the number right. Okay, so this is minus 21.25 Kelvin, right? So what this means here is, again, it's constant. So the thermocouple is always colder than the surrounding T infinity, than the liquid here, right? And it's colder by 21.25 degrees here. So again, that's useful information, because you can see in this situation, if you knew that, you would be able to compensate for that maybe in software here. But again, make a note here that this is going to be a function of how fast you're increasing here, right? How fast the water is increasing. So if it's increasing at 5 degrees a second, this thermocouple is going to lag by 21 degrees here, okay? So I'll tell you what, this might be something that's interesting to maybe hop over to Mathematica. Let's hop over to Mathematica and maybe verify this by direct calculation, as well as maybe plot the response of the water temperature, and also plot the response of the thermocouple temperature, and just see what does the steady state error look like. Okay, so let's go ahead and check that the system response to a ramp input yields constant steady state error. Right, okay, so if you recall, the differential equation, right, that we derived earlier was this. So now, if the input T infinity is a ramp, this is now a ramp of slope A. There we go. So now, let's go ahead and take the Laplace transform of both sides to get the response in the Laplace domain. So here we go. This first term is ST of S minus T0, right? Plus beta T of S is equal to beta A over S squared. Great. So now solving for T of S yields, and I actually have that already prepared so I don't mess the whole input up trying to plug it in. Now here it is in the Laplace domain. I want this in the time domain. So let's go ahead and just inverse Laplace transform that thing, right? Beta A over S squared plus T0, this whole thing. is over S plus beta. And now let's go from the S to the time domain, and this gives me the temperature in the time domain. So shift enter that here, and here we are. This is the temperature here in the time domain. So now let's go ahead and plot this with an initial condition of what we wanted earlier, right? So I think we said for this thermocouple, we said it started at 25 degrees Celsius plus 273. This just gets us, I believe, to 298 Kelvin, right? Okay, so let's go ahead and plot. How about T of T? But I got to make some replacements here, right? So A is going to be 5 degrees per second, right? T0 is going to be 298 degrees here. And then beta, I think we said was what, 4 over 17, right? And let's plot this from time equals 0 to 100 seconds just to see what it looks like. So there we go. So here's what the thermocouple is going to do here. It might give us some insight here if we plot this also against the input ramp here, right? So the T infinity input was just what? It was A times T, right? It's a ramp of AT. And again, let's replace A with 5, right? Because it's 5 degrees per second. So now if we shift enter that, here we are. This is what this looks like here. And you can see that the temperature of the pot of water is just rising at a constant 5 degrees per second here. And what actually happens here is that, look at this. Again, you can see the steady state behavior. There is zero steady, a constant steady state error here. And the magnitude between these is about 21 degrees here, right? Okay, so there we are. That, I think, ends this example. Let's jump over and take a summary of what we've discussed today so far. All right, so to summarize what we discussed today, we first introduced the concept of time domain analysis and saw that what we're really trying to do here is predict the response of the system without having to explicitly calculate the actual analytical response. We then discussed a little bit of the difference between the transient and the steady state behavior system and why the two are important to differentiate between. We then looked at a first-order system as a starting example, and we saw that a first-order system could be subjected to different types of inputs. The first thing we looked at was a step response, and we saw that if you had a first-order system with a step response, you could start talking about things like what's the steady-state error of that system to that step response, as well as what's the settling time and the rise time as two other additional performance metrics to measure how does the system respond to this step. We then looked at how this was also a little bit different if you looked at having a ramp response. Now, we also showed that, you know what, with a ramp response, you can also define a steady state error. You actually could probably define a settling and a rise time as well, but it gets a little bit more unclear there, so we didn't actually focus on that. Then what we ended up doing to tie all this together is we looked at an example of a first-order system and its step and ramp response using a thermal system. So, I hope this gives you a little bit of an introduction to time domain analysis. Note that we only did a first order system here. This is a little bit of a teaser for our very next video where we start looking at second order systems, and we see that it gets a lot more interesting with a second order system because we can start defining other time domain analysis and other performance metrics like percent overshoot and other interesting behavior for more complicated systems here. So that's coming up with our next video, and I encourage you to watch that if you are interested. With that being said, if you enjoyed the video today, please go ahead and like and subscribe to the channel here. It really helps me keep making these, and I hope to catch you at a future video. Until then, I'll talk to you later. Bye.